I hope you enjoyed all of the exercises from chapter 9. Here we are with exercise number 7. This is the last exercise in this chapter. Here we will explore the R matrix that comes from QR decomposition. In particular, I have set up this exercise to help you understand how to use QR decomposition for least squares computations. Least squares is one of the most important applied linear algebra techniques for statistics and therefore also machine learning and basically anything in data modeling or data fitting. So least squares is all over the place in data science and statistics. Now, I'm going to talk more about least squares in chapter 12. So you're not going to learn the least squares algorithm here in this exercise, but there are ways of understanding how to use QR decomposition for least squares. And once you get through this exercise, you're really going to understand this technique, how to use QR decomposition for numerical stability of the least squares solution. In particular, we want to start with a tall matrix. So create a matrix A that is tall and full column rank. And what you are going to see when you compute the QR decomposition and look at the R matrix is that it is upper triangular, of course, because all R matrices are, but only the first n rows are actually non-zeros in this matrix. All of the later rows are zeros. So you want to confirm this in Python using a 10 by 4 matrix. Two things. You want to make sure that this is a random numbers matrix so that we get a full R. And you also want to compute the full QR decomposition, which is also sometimes called the complete QR decomposition. That requires an extra input into the QR function in Python. Now, a little bit more about R. It's non-invertible because it's rectangular for this case, for tall A. But that little submatrix at the top is square and full rank, and so it is invertible. And so then what you want to do is compute the full inverse, the explicit inverse, not of the entire matrix R, but just the first n rows. So only the rows of R that are non-zero, that contain non-zero elements. And then you want to compute the pseudo inverse of the full R, which of course is the same thing as the left inverse, because we are assuming that this is a full column rank matrix, and then basically just compare these. Okay, so now I will switch to Python and walk through my solution. So here I have a random 10 by 4 matrix, so a tall matrix that is full column rank. And you can see, as I suggested when I was talking about this in the book, we have R contains lots of zeros, but if you look at the first n columns, so in this case n equals 4, the first n columns contain non-zero values, and everything else, everything below that is just all zeros. Okay, by the way, I discussed this earlier in the chapter, but just to show you again, I can get rid of this. So here you see R is the same size as A, and when we implement QR decomposition with no inputs, then Python is actually going to compute the compact QR, which is also sometimes called the economy QR. And here you see we get only the rows with non-zero values. Now, it looks like these numbers are different from what I just ran previous time. They are, in fact, identical, but the matrix has changed. So let's run this again just to show you. Here's this. And now I'm going to, actually, let me do it this way. And now I'll comment out this line. So now this is the complete or the full QR decomposition of this same A matrix, because I'm commenting out this line. And you'll see if you look at these numbers here, then you see we run it again, and those numbers are exactly the same. So the QR decomposition is the same. Just, the question is whether you have all these additional zeros on it. So now what we're going to do is extract this sub matrix, this 4 by 4 submatrix. And we know just by eyeballing this, that this is going to be invertible. It's square because it's just the 4 by 4 submatrix. And we know that it's invertible because we can see that all of the diagonal elements are non-zeros, and every triangular matrix which has non-zero elements in the diagonal is necessarily invertible. So even without computing the rank or the determinant or anything fancy, we just look at this matrix, this submatrix, and we can determine that it has a full inverse. And that's what I do here. So here I take just this submatrix here, I call this R sub. I compute its inverse and then the pseudo inverse of the full matrix R, including all of these zeros. Now, this is equal to the left inverse. So you could also compute the left inverse of this matrix. Okay, and then we're just going to print out both. And here you see that here's the full inverse of that submatrix. Here is the left inverse of R. And what I want you to notice here is that this full inverse of the submatrix and the submatrix of the left inverse are identical. They are the same. The only difference between these two results is the left inverse has all these extra columns of zeros. Otherwise, these are the same. Okay, so I hope you enjoyed working through this exercise. The concepts from this exercise will return in chapter 13 when I introduce you to the least squares algorithm and using QR decomposition to implement least squares.